So we've introduced now polynomials as a formal object. They're just symbols that are, as we've been playing with, right? Sum of sum of coefficient times power, such that eventually the coefficients are all zero. That's what a polynomial is. Now, when you take calculus and whatnot, you think about polynomials as functions. That is, they're ways of taking usually the real numbers. In our case, the field of interest is the complex numbers, but they're ways of taking those and producing other numbers. Okay, that's a polynomial function. These are different things. The polynomial itself, this guy, this is just a formal symbol. A polynomial function, well, is firstly a function, and secondly, a function that's built using scaling and powers and sums. But it's firstly a function. Our polynomials are not functions, they're just symbols. Now, our symbols we can use to define functions, but as we've been dealing with them, they are very much not functions, and we need to be careful. And I'm going to tell you exactly why we need to be careful. Let's work outside of C for a minute. Let's leave C alone for a second. And let's look at F2. F2 is 0 and 1, or it's Z mod 2. However you want to think about it. I want to think about it as a field, so I'm going to say it's F2. Okay, just like we considered polynomials over C, we can consider polynomials over F2. Okay, so we'll use the same symbol, F2 adjoin T. What do we know about this? Well, I know that T to the N is certainly there for any power of any non-negative power N. So in particular, there's at least as many polynomials over F2 as there are natural numbers. In fact, they have the same cardinality. But I just want to point out that the set of all polynomials there's infinite number of them, right? So collection of all polynomials is infinite. All right. Let's now let S be the collection just of all functions from F2 to F2. So what does it mean to define a function from F2 to F2? Well, you got to send 0 and 1 somewhere. How many options do we have to send 0? Well, we could send 0 to 0, or we could send 0 to 1. How many options do we have for sending 1? Well, we could send 1 to 0, or we could send 1 to 1. Either is fine. So in particular, if we were to do a counting method, 0 has 2 possible outputs, and 1 has 2 possible outputs, for a total of 4 different ways of sending 0 and 1 over to 0 and 1. So the collection of all functions, which is S, has size 4. So the cardinality of S is 4. Certainly, 4 is not infinite. That would be a big problem. And so the functions, just functions, not even specifically polynomial functions. It turns out all functions this way are polynomial functions, but just functions, period. Not restricting to 2, just function. There is only 4. Whereas polynomials, so symbols in these symbols that we're dealing with, there's an infinite number of them. And so we can use polynomials to define functions, certainly, but we have to be very, very careful in general on that relationship. That relationship is not in general a one-to-one relationship. So we must be careful. However, in this class, it is a one-to-one relationship. So proposition. Two polynomials, f and g over, we're going to use C. If it's true over C, it will be true over a subfield of C. That I don't think what I just said follows exactly, but in characteristic 0 it is true. So, uh, so two polynomials over C are equal as polynomials if and only if they're equal as polynomial functions. From C to C. All right, proof. Well, if f equals g as polynomials, so formal symbols, then the functions are just the same thing, are identical. The reason being is f and g are just the same expression. You can't distinguish them symbolically, so the functions they define are going to be the same. Sometimes on the on the function side though, sometimes two functions look different, but they happen to be the same function. So we have, there has to be some care taken in general, but if they have all the same coefficients, the functions they define must be the same. All right, so that's the forward direction. So we did that one. The backwards direction takes some work, and it should take some work. The reason why it should take some work is because, as we saw, it's false in general. There is no way for these to be equal. For example, the polynomials t to the n all define the same function. But they're all different polynomials. Why do they all define the same function? Well, what happens when you raise 0 to the nth power? You get 0. What happens when you raise 1 to the nth power? You get 1. So they all define the function 0 goes to 0, 1 goes to 1. As long as n is bigger than 0, of course, for n bigger than 0. But they're not equal. So this second part is going to take a little bit of work because it's not true outside of C. Okay. So let's say that f and g are polynomials that define the same function. We want to show the coefficients of f and g are the same. That is, they're the same polynomial. So that is honestly the reverse direction. Okay. We're going to replace f and g with the difference of them, and instead show that if h is the 0 function, all coefficients of h are 0. Right? Because if f and g are equals as functions, f minus g has to be the 0 function. And what do we want to show? We want to show all the coefficients of f and g are the same. Well, that's if we want to show they're all the same, then if we look at their difference, the difference should be 0. And that's an if and only if. So that's equivalent to showing that all the coefficients of h are 0. So that's what we're going to prove instead. So we're going to we're going to proceed by induction. And we're going to let P of n be the statement f of t has degree n, f of t equals 0 for all t and c. Okay, so we have a polynomial of degree n, we're inducting on degree, and we're assuming it's the 0 function. So whenever I plug in fact, let me not even use t because t gets used a bunch. Let me say f of z equals 0 for all z and c. Then f is the 0 function. Okay, so this is our inductive statement. Let's prove it. So the base case, and I'm not sure if I need both 0 and 1, so let me just do both 0 and 1. So p of 0, well, if p in degree 0, the only functions of degree 0 are possibly of degree 0 are constant polynomials. And the only constant, which is the 0 function, is 0. So this is fine. And p of 1, which is a linear polynomial, so something of degree 1, is 0. So the line is the 0 function if and only if of course, the slope and the y-intercept are 0. So P of 1 is also fine. Also works. Is also true. Fine is not mathematical. Sorry. There's not really anything to do there. Okay, so the base case is clear. All right, for the inductive step, suppose that P of n minus 1 is true. And we're going to write f of t is an t to the n plus a1t plus a0. Since f is 0 for all inputs, it's 0 when we plug in 0. So, on the one hand, let me give myself a little bit of space. On the one hand, we get 0 when we plug in 0. On the other hand, we can certainly plug in 0. And what do we get here? We get that 0 is a naught. Great. So we can write f as, well, an t to the n and a1t. There's no a0 term, but we can also factor out a t. All right, and what do we know? Well, we know that f of z is 0 for all inputs. Let me be really explicit here. Let me actually call this something, this bigger expression something. Let's call this g. We know that when we plug anything into f, we get 0. And in particular, if the only time that we have that the g of z is maybe not 0 is if z is 0. And so g of z therefore must be 0 for all z not 0. In particular, when z is not 0, you can divide by it and get that g of 0. The only possible place where g of z might not be 0 is at 0. Okay. What must happen here? Well, since polynomial functions are continuous, g of 0 actually has to be 0. And if you care about the more, and so why is that true? Well, obviously, if polynomial functions are continuous, you can't go from being 0, 0, 0 and then have a jump at 0. That's break in continuity. But a more specific analytical argument, which it's not a class in analysis, but you might say take a sequence that goes to 0 where Zn is not 0 for all n. Any sequence, like 1 over n, does the job. Then g of Zn goes to g of 0, but g of Zn is identically 0 because all the inputs are non-zero. And so the sequence g of Zn is the sequence 0, and the sequence 0 must converge to 0. But limits of sequences are unique. So g of 0 equals 0. All right. We don't care about the analysis. We'll just rely on continuity. But if you cared about that, that's there. Okay, so again, this was a longer video. Sorry about that. But what we've seen is the assignment of polynomial to polynomial function is one-to-one. Namely, if you can't send two different polynomials to the same polynomial function, and so on. It is, however, not true in general that this assignment is one-to-one. But what this proposition allows us to do is it allows us to freely interpret polynomials as polynomial functions and conversely. As polynomial functions. So we're going to go back and forth between the two as if they're the same thing, but we have to be careful that they're not in general the same thing. All right.